So your homework assignment for this weekend is going to be practice problems on page 99 to 101, number 23, number 26, 27, 29, 31, and 32. Remember that number 32, you were getting no setup help, and yes, you are expected to at least attempt through the setup and beginning portions of solution all 6 of the problems. So let us begin. If we start with number 23, you're going to notice that I have the diagram from the textbook copied down onto my paper. You should have the same when you set up the problem. Another thing that you're going to notice when you solve these problems is take a look at this. I have a separate sheet of paper for each of these problems, which means that when you do this, you should probably likewise provide yourself plenty of space to organize your work completely. So, problem number 23, it says, Arlene is to walk across a high wire strung horizontally between 2 buildings 10 meters apart. The sag in the rope when she is at the midpoint is 10 degrees, as shown. So here we're going to say that the sag in the rope right there is 10 degrees. If her mass is 50 kilograms, what is the tension in the rope at this point? So a few important things that we want to remember. If her mass is 50 kilograms and we're solving for her force of tension, that means that Arlene here is our object. So that means that if we're going to solve for this, we're going to make sure that we draw a free body diagram of Arlene. If we're going to solve for a free body diagram of Arlene, we have to decide how many different forces are acting on her. And the first force that's acting on her would, of course, be her force of gravity, or her weight. Additionally, we know that Arlene is at the midpoint and that she is being held at the midpoint by one rope pulling on her into 2 different directions, which means that the force of tension on this side is holding her up against gravity, and the force of tension on this side is also holding her up against gravity. Please note that when I draw these arrows on this diagram, I have not done a free body diagram. The free body diagram would be done separately here, and it would in fact mean that you would have to do a separate diagram showing all of your arrows. We are going to be using Newton's first and second law to resolve this free body diagram. So once you get your free body diagram drawn, we're going to consider that the sum of all forces on Arlene is going to be equal to mass times acceleration. And if you take a look, you can tell that all of the forces are happening in 2 different dimensions, which means that you're going to have to separately resolve the sum of all forces in the x direction and the sum of all forces in the y direction. And both of those forces will equal mass times acceleration, which means that you're going to have to figure out from your free body diagram that includes the force of the rope balancing her out and her weight pushing down, what the components in the x and y direction are going to be. Now remember, I did also say that you were going to be taking a look at Newton's first law, which says that an object that is experiencing uniform motion, or if that object in that frame of reference is at rest, the sum of all forces equals 0. Make sure that you consider that, and you consider how that would relate to finding the net forces in the x and the y direction in order to completely solve for this problem. I do recommend that if you are still stuck at this point in time, that you actually draw the free body diagram and then listen to the part where I describe what Newton's first and second law have to do with each component in the x and the y direction again. And that's your basic setup for problem number 23. Problem number 26. It says, a person pushes a 14-kilogram lawnmower at a constant speed with a force of 88 newtons, directed along a handle which is at an angle of 45 degrees to the horizontal. And it gives you that figure 4-45 is that figure. And so I have a version of figure 4-45 drawn right here. And if I thought it was important enough to draw, then you probably could guarantee that you should also think that it's important to draw. One of the things that I add to my figure right now, and I wanted to make sure that I did it so that you could visually see it, is that this is the direction of the force. Remember, a picture is not a free body diagram, but it's a great place to start when you consider a free body diagram. Now, once we know that this is our picture, we want to make sure that, hey look, the very first thing it asks us to do is draw a free body diagram, which means that you would consider the spherical cow version of the lawnmower, where the lawnmower is a point-like object and we have to consider all of the forces that are acting on it. And here's where the picture is incredibly helpful, because I know that this lawnmower happens to be mowing the lawn, which means we're on the surface of the earth, which means that this lawnmower is experiencing the force of gravity. I know that this lawnmower is on a surface, which is another way of saying that it's one surface in contact with another surface. So this lawnmower is experiencing a normal force. And I know that this lawnmower is getting pushed in a forward direction. So I know that this lawnmower is experiencing a force that is at an angle downward of 45 degrees, just like it's shown in the picture. Last but not least, I know that this lawnmower is experiencing constant velocity, which is another way of saying that this lawnmower is experiencing uniform motion. And I know that if the lawnmower is experiencing uniform motion, that the sum of all forces acting on it must be 0. And if the sum of all forces acting on it must be 0, that means that in both the x and the y direction, all of my forces better add up to 0. And I know that I have this force right here, which is going to have a horizontal and a vertical component. I can guess that the vertical component might be taken into account when I'm finding my net forces using the weight and the normal force, but this horizontal force right here, as it's drawn, has nothing to balance it out so that the net force is equal to 0, which suggests that somewhere in this diagram I have another force that's a resistive force that would balance out that x component of that force. And lo and behold, that force is friction. So that means when I do my free body diagram for A, I'm going to be including weight, normal force, applied force, and friction. And anytime I do a free body diagram, it should be drawn as much to scale. You should set up your axis, and remember, you want to make your axis as easy as possible. You want as many forces as possible to lie on your x and y axis, so once you draw them out, you can visually see what the best axis you should draw is. You should establish your positives and your negatives for your forces, and then once you've done all of that, it would be really wise for you to figure out what your forces in your x and what your forces in your y direction are, because both of those forces, according to Newton's second law, will equal mass times acceleration. And you also know, according to Newton's first law, that if the object is experiencing uniform motion, which it is in this situation, that the net force should equal 0, so mass times acceleration should, in theory, equal 0. Once you have all of this done, it should be no problem for you to solve for B, the force of friction, by resolving your net forces. Once you've done that, it's again, after you solve for friction, should be just a matter of studying your net forces to allow you to solve for the normal force, which is part C. Once you've solved your free body diagram, resolved your forces in the x and the y direction, solved for the force of friction, solved for the normal force, you should be able to apply what you know to a different situation. Question D asks, what force must the person exert on the lawnmower to accelerate it from rest to 1.5 meters per second in 2.5 seconds, assuming that there is the same friction force? That means that in part D, it's actually changing your applied force Right, which means that you're going to be taking that free body diagram and creating a new situation where your constant velocity or uniform motion is no longer true. What it does give you instead is it says that the lawnmower accelerates. That's how you knew it was no longer uniform motion. But it doesn't give you an acceleration. Instead, it says that the lawnmower starts at rest, accelerates to 1.5 meters per second, and that occurs in 2.5 seconds, which means that it gave you a V0, a V, and a T. And this should be a huge clue. It should tell you that before you can solve for the applied force, you're going to have to solve for the acceleration using kinematics. At that point in time, you might have to take a look at resolving your forces. If you're resolving your forces, it's really important. It tells you to assume that the force of friction is the same force of friction that you used to solve for B. With that information, you should be able to solve number 26. Moving on to look at number 27. Again, I've copied the figure from the textbook, just as you should do. And the figure here is figure 4-46. And the problem says 2 snowcats tow a housing unit to a new location at McMurdo Base, Antarctica, as shown in figure 4-46. Draw figure 4-46. The sum of the forces FA and FB exerted on the unit by the horizontal cables is parallel to the line L, and FA equals 4,500 newtons. Determine FB and the magnitude of FA plus FB. So they're telling you that the force exerted on the house by the tension force in FA and the force exerted on the house from the tension FB will result. That means you know that the resultant vector, the sum vector of both of those forces, is parallel to line L. And that's a huge critical piece of information, because if you're going to draw a free body diagram for the house, and you're drawing all of the forces that act on the house, and you know that the house is accelerating, the sum or resultant force is going to be along that line L, then you should have no problem considering what your components Fx and Fy are, especially since you know that Newton's second law says that they're equal to mass times acceleration, and you know that the resultant vector is a result of the x and y components. Once you've established that and you've considered both Newton's first and second law, you should be able to, if you're given that the force of tension from object A is 4,500 newtons, you should then be able to solve for the force resulting here and the sum of those two forces, aka the resultant vector that's parallel to line L. Moving on to problem number 29. I particularly like this one. You've got a window washer pulling herself upward using the bucket pulley apparatus shown in figure 4-48. That means that this is my artistic rendition of 4-48. As I've drawn it here, so should you draw in yours. Alright? It says, how hard must she pull downward to raise herself slowly at a constant speed? So that's a really important thing to consider. Right? When she pulls down with her hands, right, she's causing tension in this rope, which means that we must be assuming that the cord is massless. We get to ignore the mass of the cord. And that the pulley has no friction. And if we assume that, then we know that the force of tension that she causes by pulling down here should be equal to the force of tension here, which is causing her to move up, and that's how the pulley system is working. Alright, that means that we actually, in this problem, have two objects. So we should be solving a free body diagram for each of the two objects. One of those objects should be you in the bucket, and one of them should be your hands. You need to consider in these situations what information you could use to solve this problem. You know that she wants to move with a slow, constant speed. Just a warning, if it's a constant speed, it's a uniform motion. The uniform motion means that the net force in any direction is going to be equal to 0. And this word slow right here is just added in there to throw you off, because it doesn't matter if her uniform motion is slow or fast. That would really just depend on your frame of reference. So make sure that you're focusing on the fact that it's a constant speed, and that means that the net force that she experiences is going to be equal to 0. Then once you solve for that, and once you have your actual force, you're going to take a look. If she increases a force by 15%, what will her acceleration be if her mass is 65 kilograms? So here you have to consider, if the force that you solve for here, you're going to get an actual force that she applied. Right? If we take that force and we increase it by 15%, that means we're going to take that force and we're going to add 15% of that force to it to get your new force. Right? Another way of looking at that is saying that we're taking her force and we're multiplying it to increase it by 15%. So we're multiplying it by 1.15 to get her new force. And if we have that new force and we know that her mass is 65 kilograms, then we should have enough information to solve for acceleration, because we know that acceleration is directly proportional to force, and we know what the relationship is there because that's Newton's second law that we can use that will allow you to solve for part B of problem number 29. The last one that we're going to take a look at from a setup perspective is problem number 31. Problem number 31 is a hugely important problem. Tip here, this one shows up on quizzes and exams everywhere. One of my favorite things about this problem is that you have no numerical values, which means you're going to be solving exclusively using variables. Another thing to note there is if you're solving for variables, that means that your calculator is useless, and all you're going to be using here is your concepts, Newton's first and second and third law. So it says that figure 4-49, which I've drawn here, and you should also draw, shows a block of mass A right here, and it's on a smooth horizontal surface. So one of the things that you can assume is since this is a smooth surface, you can assume that you can neglect friction. Alright, this block is on a smooth horizontal surface, you're neglecting friction, and it's attached to a cord. We may assume that this cord is massless, and that this pulley is frictionless, but it's attached here to another box which is suspended, and that box that's suspended hanging vertically is experiencing force of tension upward and the force of gravity downward. This box right here should in theory be experiencing a weight downward, a normal force upward, and tension outward. If this cord is massless and this pulley is frictionless, then you should know the relationship between these two tensions. That means that you're going to have to solve for a free body diagram for A and B. And once you've done that free body diagram for A and B, you should resolve for the X and Y components of forces for A and B. Once you've done that, you should easily be able to find the formula for acceleration and find the formula for tension for both box A and B, using the relationships that you know are true anytime you've got a massless cord on a frictionless pulley that is pulled taut the entire time, pulling 2 boxes at once. And that is the last problem that you're going to be doing with guidance, which means that problem number 32 is entirely up to you. But you're going to notice that through every single one of these problems, what do I suggest that you do? I suggest you draw a free body diagram and you resolve your components of forces, apply Newton's first and second law. Here again, I ask you to draw a free body diagram, resolve for your net forces, and use Newton's first and second law. Here again, draw a free body diagram, resolve for your force components, apply Newton's first and second law. And here, you're going to draw a free body diagram, resolve for your forces, apply Newton's first and second law. And, oh my gosh, look again. We did a free body diagram, we resolved for our x and y components of our forces, and applied Newton's first and second law. So you better believe that when you do number 32, you're going to draw a sketch, figure 4-50. You're going to draw a free body diagram. You'll resolve for your x and y components of your forces. And then you will solve for the unknown values, applying Newton's first and second law. I wish you the best of luck. Please make sure that your attempts in these problems are complete and that you have them prepared for class, even if you don't submit them until after class. It's really critical that we use what information we have at this point in time to move forward with the lesson, because we're just going to be lab after lab after lab as soon as we reintroduce friction.